Hello, everyone. Welcome to join our session, Coldplay Liquid Cooling Design for OAM and OAI. So my name is Shuai Shao from Baidu. Cheng Chen, who is from Facebook, will be together with me to present the content of this session. So for cooling workstream under OAI, we are focusing on thermal management of OEM products and OEM-based platform. Previously, we contributed the air cooling solutions and specifications to the community. That thermal solution can support 450 watts OEM. Now, we are exploring cold plate liquid cooling solution aiming at as high as 700 watts. So we are going to present 4 topics in this session. The challenges that we considered for OEM and OAI, and the cold plate and its interface design for OEM products. And then 2 cases for the liquid cooling modules. And last, we're going to talk about the cold plate liquid cooling specifications that we are working on. For OEM, the thermal performance of an air cooling heatsink may reach a bottleneck as the power density of OEM keeps increasing in the future. Second, OEM products from different vendors require a certain amount of redesign efforts for cooling solution, and also a certain amount of resources are needed to achieve the required level of reliability and serviceability. So those challenges increase the complexity for engineers to adopt liquid cooling for OEMs. And on a system level, there are also some challenges that we saw and we are facing with right now. First, how to make the liquid cooling solution has a better serviceability for end users and a better manufacturability for suppliers. Specifically, we believe that we should properly design how to let the cold plates, quick disconnects, and server manifolds be assembled as a module. And once it's assembled, this entire module should be installed and serviced in the chassis in a convenient way. That additional modification on the chassis should be as fewer as possible. One reliability concern is the fluid. Good compatibility between the fluid and the hardware can avoid issues such as galvanic corrosions, fouling, scaling, and micro-based growth. And the other concern is the design for the leakage detection and the leakage intervention. So the third one is ecosystem. We would like to see more players in join these areas, including more end users and more suppliers from component level to the system level. The last one is the use cases. For example, we need to consider the variation in the OEM cards and the baseboard layout, the variation in requirements on the operating conditions for different data center facilities. Having those challenges in mind, now please allow me to let Chen describe the scope of our OAI cooling workstream.
Thank you, Shuai. This is Chen from Facebook, thermal engineer. I'll take on the following slides. Yeah, so given the challenges that Shuai described, we built the OAI cooling workstream under the OAI subgroup. Our target is really to develop the specifications, guidelines, and share the best practice for enablement of liquid cooling solutions based on OEM products and the OAI systems. We're trying to tackling those challenges from 5 perspectives. The first being the OEM interface, that is the thermal and mechanical interface between the OEM products and the cold plate solutions, including the thermal interface materials. Second will be the OEM cold plate. We want to design a cold plate or define our cold plate specification that will serve the purpose of cooling up to 700 watts OEM products. The third one would be the cooling module that is a passive cold plate loop assembly, which is basically dealing with the coolant distribution and the serviceability and assembly at a system level. The fourth one would be the interchangeability. That's an ideal goal for the potential customers and suppliers, where we can start interchange our cold plate solutions with other 4 different OEM products, all being used in different OAI systems. Last will be define all the guidelines for the materials selection, the validation of the liquid cooling solutions, including the entire system, and how to maintain them in the infrastructures. Next page, please. Yeah, so if you only look at the component level cooling options, looking at the OEMs, as the power of the OEM grows, we have to use different cooling approaches. This figure we have presented in the OCP Regional Summit last year and the Global Summit this year. Basically, starting from lower power to higher powers, we will have the reference heatsink solution for the air cooling, which is baseline, and we can increase the cooling support capability by 20 to 30% using the closed loop liquid cooling solutions. And beyond that, when we're trying to solve something that's 60% higher than the baseline OEM power, we would like to introduce the cold plate solution into the system. And you can see the Elton system assembly picture over on the lower right side. That can be coupled with either a rack level heat exchanger or in-row heat exchanger or even facility water, depending on each hyperscaler's infrastructure capability. Next page. Yeah, coming to the OEM interface, we have been exploring different ideas, trying to accommodate the different OEM products and solving all the challenges we described before. One idea is the heat spreader concept for the bio-die OEMs, and unfortunately, it doesn't apply to the linear OEM, which has to be done in another approach, and which we think is the linear surface and the stiffness surface standardization. Now, if you look at the heat spreader concept for the bio-die OEMs, it uses a heat spreader to interface between all the components and the cold plate. You avoid direct contact between cold plate and die. You're making standard assembly and universal cold plate possible. The cons of it is to introduce additional thermal surface material, increase the thermal resistance. However, we believe this can be compensated by the superior performance of the cold plate. Next page, please. Yeah, so if you look at how the cold plate be mounted into the OEM products, you're adding the cold plate itself to the spreader plate and then to the OEM product. By doing this way, you are absorbing all the power or heat generation of the components on the OEM PCB into the spreader plate, and it will be taken away by the cold plate. The cooling performance of it is to support up to 700 watts with a heat exchanger or facility water. The pressure rate, the flow rate and the pressure drop are designed to be within typical pumping unit's capability. The mechanical interface of it will be considering the assembly procedure and the thermal interface material performance. I also want to enable the interchangeability when it comes. Next page, please. So this is a case study based on Facebook's OAM platform. In this system, it's a very typical OAM-based platform. It has 8 OAM mezzanine form factor cards, 2 passive cold plate loops, and the board and the cold plate assemblies are front accessible. And so for this particular system, for this particular case study, we use manually mated QDs. It's designed for easier assembly and serviceability. And in the future, we'll also explore the design solutions for the blind-mate QTs. So if you look deeper into the details of cold plate assembly, you will see that from top to bottom, it has a metal assembly, it has a cold plate, OAM, and baseboard. So the metal assembly here is used to help assisting the serviceability of the cold plates. So we're trying to design something that one technician alone will be able to handle in the data center environment within reasonable time window. Next page, please. Yeah, so this to describe it, to show a service condition for the passive cold plate loops. Imagine one of the OEM card is broken and you need to replace it. In heatsink scenario, it's very easy. You just treat it together as heatsink as screw. You remove 4 screws from the baseboard and you take it out. You add the new assembly, and that's it. But for a system with cold plates mounted, because the cold plates attached to a external loop, you cannot remove them as simple as that. So the target is really to minimize the steps we need to take, minimize the number of screws we need to attach. Here in this condition, we're showing that by flipping up the sheet metals, we are able to deal with only 2 OEM cards, and you can perform the service there. The entire baseboard can be removed from the front, and we can take them on the bench and service it. So this idea is still being, we're still fine-tuning to make it to a more material level of design, and we'll share more complete design files and guidance with the OCP partners once it's being accomplished. Okay, for the following contents, I'll pass it back to Shuai. Thank you.
Thank you, Chen. So I will just continue. So in this slide, I'm showing the second cooling module case study. There are 3 highlighted features in this design that we are working on. So we will install the entire system as a one module into the chassis, including cold plates, quick disconnects, and the servo manifold and other parts. And we design a panel for leakage protection. All the hoses connections are designed to be above the panel, so any liquid leakage can be accumulated by the panel. And the third one is the margin of the panel is designed to be as small as possible. For highly populated GPU baseboard, this design is to avoid the structural interference with other parts on the board. So in this slide, so we are showing the ongoing specifications for the cold plate liquid cooling. So it's based on the contributors' experience and lessons learned from the engineering practices. So for the cold plate, the mechanical interface is defined, including some key dimensions and some the thermal parameters, including the thermal resistance and the flow impedance, are also to be defined. On the system level, the operating parameters such as the flow rate, the hydraulic pressure, and the fluid temperature are to be recommended in the practical ranges. So in the next step planning is summarized in this slide. So except the liquid cooled OEMs, other parts in the OEM systems are still meant to be air cooled. So we are planning to provide a complete thermal and mechanical design for the this hybrid cooling solutions for the OAI system. We are to provide universal OEM cold plates and OAI cooling module designs with customization. So then we're going to release a comprehensive specifications and the reference designs based on our case studies. So we certainly can use the help from the community to fulfill our plans and achieve our goals for OAI cooling. So if you are interested, please contact me and Chen and join the mailing list. And you can find the additional information from the link showing here. Thank you very much.
Thank you, Shai.